So we are looking at membranes. This is part 3 of membranes. And just to loosely describe the big picture of what we're going to talk about and how it's different from the first 2 parts of membranes. So in part 1, we talked about the structure of the membrane. In part 2, we talked about transport, the forces that move things across the membrane. We looked at passive versus active, etc., and some of the players that had to facilitate movement. Now in part 3, we're going to talk about how movement applies to water. Okay, now water goes freely through the membrane, right? So water is not going to follow some of the active, passive, principles that we talked about before. It's not going to require any carriers, but it will require a gradient. And so we're going to talk about how that is important and how that allows water to move by a process called osmosis. We're also going to talk about some of the other structures of epithelia toward the end of this part 3. Okay, so just kind of carrying on the conversation as far as membrane transport. Let's look at lecture objective number 1. So explain how a difference in solute concentration across a membrane can cause the movement of water, and explain the distinction between the osmolarity and the tonicity of a solution. Okay, so those are 2 terms we're going to want to describe and then distinguish from each other as well. Osmolarity versus tonicity. Now, as we speak about the movement of water, this has a unique term. This is called osmosis. And so it's basically the movement of water through a membrane that allows for that. And it's always going to be passive. So it's always going to be down the concentration gradient. It's going to be unaffected by things like the charge, the polarity of the cell. So it's going to not at all obey or be impacted by the membrane potential. So remember, we talked about the membrane potential. Inside of the cell is negative, outside of the cell is positive. That doesn't matter when we talk about water movement. Always it's going to be driven by the concentration gradient. And in order for us to think about the concentration gradient of water, it's important for us to think about where the solutes are, right? If we have any solution, it will have a certain amount of water and a certain amount of dissolved solutes, right? And so in order to think about where the concentration of water is highest, we have to think about how much solutes are dissolved in that concentration versus the other area or the other concentration, and that will determine what direction water will move in. If we look at the illustrations here on the right, so in panel A, we've got a solute concentration inside this cell that is about 300 milliosmoles, right? And that means that this has an osmolarity of about 0.3 moles. Okay, now if we think about its water concentration, because 0.3 moles of particles are dissolved in the solution, we now have a water concentration of about 55.2 moles. If we think about the external environment, so what's happening outside the cell, and we compare that to what we just described inside the cell, the outside of the cell has 0 moles. So there's pure water on the outside of the cell. 0 solutes are dissolved in the solution on the outside, whereas the water concentration is going to be slightly higher now. It's going to be 55.5 moles. So just comparing those 2 solutions, we can already detect a gradient for water. Water is at a higher concentration on the outside of the beaker or the cell. It's at a lower concentration purely because we have solutes that are dissolved in the solution now. And so now the gradient for water movement is from high concentration on the outside to low concentration on the inside. So water will move into this cell. If we compare that to what's happening in panel B, we have a higher solute concentration on the outside of our cell now. So the solution on the outside of the cell is 1,000 milliosmoles. All right. The water concentration on the outside of the cell, consequently, is going to be slightly lower because now we have solutes dissolved. So that's going to be about 54.5 molar. And on the inside of our cell, the solute concentration is 300 milliosmoles. All right. And then the water concentration, again, slightly lower or slightly higher, my apologies, is going to be about 55.2 molar. So again, we have identified a water gradient. We have higher water concentration on the inside of this cell, lower water concentration on the outside of the cell. And so water will move from high to low concentration. So essentially, the best way to think about the direction of water movement is to first think about where do we have solute concentration and what is that solute concentration in comparison to the water concentration. Another way to express this is that water will move from a place of low solute concentration, which is synonymous with high water concentration, to a place of high solute concentration, which is synonymous to low water concentration. So if we think about it from the perspective of the solutes, it's low to high, right? Water movement, that is. And if we think about it from the perspective of water, it's going to be from high concentration to low. Okay. And that is basically the principle of osmosis. Now, if we think about the osmolarity, right? If we think about the osmolarity, it is the total solute concentration of a solution. Now, it's going to have to take into account all of the solute particles displaced in the water. Now, this is where the difference between the moles versus the osmole comes into play. So the mole is just purely looking at the solutes. What is the number of solutes that we have? The osmoles, or the osmolarity, is the displacement of those solutes into a solution of water. All right, so let's look at a few examples here. If we have 0.1 mole of glucose, that is just looking at the number of glucose particles. If we think about the osmoles, it's going to be 0.1 osmoles of glucose dissolved or dissociated in 1 liter of water. So here in this instance, the mole concentration and the osmolarity are the same because glucose will dissolve into equal parts in a liter of water. Let's look at another example and compare that. So if we have 0.1 mole of sodium chloride, right, NaCl, that will further dissociate into 2 different particles once it gets into water. It's going to dissociate into sodium as 1 mole, and then it's going to dissociate into chloride as another osmole. All right, if you think about that being dissolved in water. And so the osmolarity will be 0.2 in a liter of water. So we have to think about the total number of solute particles displaced in a solution of water. And so because a molecule like sodium chloride can further dissociate once it enters a solution of water, the osmolarity for that will be different than simply looking at the molar concentration. Okay, so the osmolarity will be 0.2 osmoles as it is dissolved in a liter of water. So if we think about osmolarity in our physiology, we don't usually have a single osmole. We usually look at this in the units of milliosmoles, just because in our physiology, it's usually a fraction of 1,000, right? It's usually a 1 in 1,000 of an osmole that represents the molar concentration in our physiology, in our body. So typically, if we look at the intracellular fluid versus the extracellular fluid, it's about 300 milliosmoles, right? So again, 1 in 1,000 is the units that we typically look at for our physiology. Okay, let's look at some examples of how osmolarity can change. So we can have a solution that is considered to be isoosmotic, and what that means is that it is completely the same as far as the internal solution. So here's a cell. Here is the cell placed in a solution of water. And the osmolarity of the inside of this cell, the intracellular fluid, versus the osmolarity of the extracellular fluid is the exact same. So the solution that this cell is placed in can be described as isoosmotic with reference to the inside of the cell. Okay, therefore, we're going to have one-way flux of water. So we talked about this principle before. Whenever we speak about movement or transport across membranes, there is sometimes one-way flux, but that doesn't mean there is net accumulation on either side. So some water will move out of this membrane. Remember, the membrane is freely permeable to water. So I don't want you to think that there will be no water movement. Water will still be moving in this isoosmotic scenario. However, there will be no accumulation of water on either side because there is an isoosmotic solution with respect to the inside of the cell. Now, if we think about a hypoosmotic solution, let's say we place one of our cells into a hypoosmotic solution. What's going to happen is we have less water or less solute, excuse me, on the outside of the cell, meaning that there's more water, and we have more solutes inside the cell, consequently less water, right? So on the inside of the cell, we have less water, more solutes. On the outside of the cell, we have more water, less solutes. And so here we can begin to look at that gradient, right? That water gradient. So water is going to move from a place of low solute or high water concentration, which happens to be this hypoosmotic solution. And if you think about this term hypoosmotic, it means that there's less osmolarity, less solutes. And so you should be thinking here when you see this term, there's more water, right? So that solution will allow water to move from high concentration into the cell where there is lower water concentration. And what's going to happen is the cell is going to accumulate more of this water. It's going to swell and swell and swell. It's eventually going to lyse. Lyse is referred to as rupturing of the cell or explosion of the cell. And then that will be because of the swelling that occurred. Okay, now this is what will actually happen to our cells. There can be what's called water intoxication, right? So if, for example, someone drinks too much water, that can be a real clinical presentation. There can be water intoxication. Cells can be overexposed to hypoosmotic environments, and then that can result in actual cell lysis, cell death. In terms of what that looks like clinically, that can be things like fatigue, that can be seizures, right? That can present in a whole slew of different clinical ways. If we think about the alternative scenario, so if we put one of our cells into a hyperosmotic solution, again, if you think about the terminology here, hyperosmotic, more osmolarity, more solutes. So the solution into which we place the cell has more solutes, so it has a lower water concentration. Therefore, relative to that, our cell is going to have a higher water concentration. And so what that is going to do is create a gradient where water moves from high water concentration, otherwise known as low solute concentration, on the inside of the cell out into that solution, which has a low water concentration and then a higher solute concentration. So the result of this would be a crenated cell, right? A shriveled cell, a crumpled cell. As all of that water leaves the cell, that will result in shriveling or crumpling of the cell. And again, this can, become dangerous steadily. This will be a scenario of your classic dehydration, right? If you're dehydrated, your plasma becomes really salty, right? It becomes really hyperosmotic. And so that will result in water moving from your cells out into this hyperosmotic ECF, and that will result in like muscle cramps that can also present with fatigue as well, right? So we can see a whole lot of different physiologic consequences if our if our extracellular fluid becomes either hypoosmotic or hyperosmotic. And so to maintain homeostasis, to keep the body in balance, it's really important for our extracellular fluid, I keep trying to say hyper here, our extracellular fluid needs to be the same osmolarity as what's happening inside our cells, and that's about 300 milliosmoles, okay? All right, I know that was a bit long-winded, but I really wanted to explain that as far as what osmolarity is and how that movement occurs. So if we think about the osmotic pressure, This is a reflection of the solute concentration and the force that's created to pull water. This is why I really want you to think about not just the water concentration, but the solute concentration as well. Because if we think about the solute concentration, that's a force that wants to pull the water onto that side, right, against that, that solute concentration gradient. So we can think about it as a force that would be applied in order to stop that water movement as well. Okay, and that would be a representative of that osmotic pressure. So looking at the scenario here on side one, we have a low solute concentration, 300 milliosmoles, a high water concentration, about 55.2 moles. On the right side, we've got a higher solute concentration. As we can see, more solutes dissolved. So that's about 500 milliosmoles, and then a lower water concentration as a result of that at about 55 moles. So what we can see is that the osmotic pressure is going to be the force that wants to pull water. Therefore, the osmotic pressure is going to be on side two, because that's going to be the side where water is being drawn to. Therefore, the osmotic pressure on side two is 12.3 atmospheres, right? Representing that this is a force of movement. On side one, it is 7.4 atmospheres. And so we can think about the osmotic pressure as moving against that osmotic pressure gradient. It's going to move from a low atmosphere or low osmotic pressure to a high osmotic pressure. So it's going to move from side one to side two. All right. Therefore, the gradient of movement is about 4.9 atmospheres going from side one over to side two. So there's a force that's created on side two that's pulling the water from side one, and the quantity of that force is about 4.9 atmospheres, which is the difference in the gradient. All right, now let's move on to look at tonicity. And tonicity is somewhat similar to osmolarity, but there's one crucial difference. Tonicity is only influenced by the impermeant solutes. Okay, so it's obeying the water gradient, it's movement of from high water concentration to low water concentration. And so in some scenarios, the tonicity and the osmolarity can be the exact same. But if there is a solute that cannot cross that membrane, we're going to refer to that as an impermeant solute. If there is a solute that cannot cross that membrane, the tonicity and the osmolarity will be different, right? Because the tonicity is only looking at the impermeant solutes, the osmolarity is looking at the total number of solutes dissolved. So likewise, we can think about an isotonic solution here. That is a solution where the extracellular fluid has the same tonicity as the intracellular fluid. We could think about a hypertonic solution on the right. This is if the solution has a higher tonicity than what's happening inside the cell. As we can see, it's greater than 300 milliosmoles. And then alternatively, on the left here, we could think about a hypotonic solution. That is if the tonicity of the solution is less than 300 milliosmoles, and that is referencing the 300 that is inside the cell, right? So it's a hypotonic referencing the inside of the cell. So tonicity can also change the cell volume, just the way that osmolarity can. So we can see the cell shriveling in a hypertonic solution. It will swell in a hypotonic solution. But there's only one difference. Again, with tonicity, we're only looking at the solutes that cannot move across the membrane. With osmolarity, we're looking at all of the solutes. So let's look at an example of that, because this is usually a little bit of a difficult concept to grasp. So on side A, we have a cell that has 300 milliosmoles in terms of the osmolarity inside, and then it is suspended in a solution where there is a urea concentration of 300 milliosmoles as well. So here we can think about the same number of solutes displaced. So there's 300 milliosmoles inside, 300 milliosmoles outside. Now, the difference here is that urea is able to move through the membrane, whereas the impermeate solute in purple cannot move through the membrane. So therefore, if we have water moving, urea can also be moving as well. So urea can move in and out of the cell. And so if we think about the osmolarity of the solution, it is isoosmotic, right? Because it's the same number inside and out. But if we think about the tonicity, right, we're only looking at the solute in purple. We're going to completely ignore urea because urea can move across the membrane. And the tonicity does not take into account any particle that can move. It only takes into account the particles that cannot move. So having said all of that, I want someone to predict what you think the tonicity of this solution would be if we're only considering the solutes in purple. So take a minute, think about this, and what do you think the tonicity would be? So we're completely ignoring the solute in yellow, just completely pretend it's not there. And think about both of these solutions with reference to the solute in purple only. Which of the two sides will have a higher water concentration, and will the outside of the cell be hypotonic, hypertonic, or isotonic? Any thoughts or guesses on that? Any predictions? Any predictions? I'm not seeing any. So basically, this is going to be hypotonic, right? Because if we ignore the solute in yellow, then there is no solute on the outside. And if we ignore the solute in yellow on the inside of the cell, there is only the purple solutes, right? The impermeate solutes. Therefore, when we compare the tonicity of the solution, which for our purposes has a 0 concentration, 0 osmolarity, when we compare that to the inside of the cell, which has 300 milliosmoles, right? Because we're ignoring, although this number says greater than 300, we're completely ignoring the solute in yellow, so it's only 300. And so this will be a scenario where the tonicity is hypotonic. The tonicity is lower, okay? So this is what I mean by saying that osmolarity is different from tonicity. Osmolarity looks at all the solutes, whether they can move or not. Tonicity only looks at the solutes that are impermeate or the solutes that cannot move. So this solution will be isoosmotic but hypotonic, okay?